Okay, welcome to our last full week of classes. I think we have one other lecture next Monday, and that's supposed to be to make up for that holiday Monday we had in mid-May. So this is our last full week of courses, and we are certainly in the home stretch. The light is at the end of the tunnel for sure. What you just saw there in the 10 minutes kind of before lecture started, that was a video of well, I don't want to say famous because he's not actually famous, but he's famous, I guess, within the physics teaching community. He's a famous physics instructor at MIT, retired now. His name is Walter Lewin. And as you can see there, he has a bit of a shake in his head. So he's unfortunately developed Parkinson's, which has forced him to retire before he wanted to, but he's still alive and he still advocates for physics education, and he has a lot of really nice physics teaching videos that he's done. Now, most of the videos he has are his own lecture recordings. There's a camera sitting at the back of a very, very large lecture theater, and it films him interacting with the students, and it films him on the blackboard, and it films him with demonstrations. All things we don't quite have the ability to do in this year's online class because I'm not able to get onto campus, and we don't have the equipment set up at U of T to record a lecture in the lecture hall itself, and we don't have access to campus. So we can't exactly do it that way, so we're making the best we can with these Zoom lectures. Anyway, to recap what you saw there, what Walter Lewin was talking about, was he was showing students, or I guess the audience in this case, I don't think they were students, that when you're letting an object roll down a hill, the only factor that mattered was the moment of inertia of the object. It didn't matter the mass, it didn't matter the radius, it didn't matter the length. All that mattered was the object's moment of inertia. And the first bit there, he showed a lot of different examples of various solid cylinders being rolled down a hill: short cylinders, long cylinders, large radius cylinders, small radius cylinders, but they were all solid cylinders. And each time he did it, they reached the end of the inclined plane at the exact same time. And then toward the end, he did a race with a hollow cylinder compared to a solid cylinder. And when he let them go, it was the solid cylinder that reached the ground first. And I'm not personally a fan of his explanation. I don't agree that it involves calculus to answer that. So here's my rendition. Why does a solid cylinder reach the ground faster than a hollow cylinder? Is simply because of its moment of inertia. You see that in Newton's second law for torque, torque equals I alpha, then the torque is going to be, the angular acceleration alpha is going to be the torque divided by I. And if you have a larger moment of inertia, meaning a hollow cylinder has a larger moment of inertia because all of the mass is concentrated along the perimeter. So if you have a larger moment of inertia, you have a larger denominator, torque over denominator, torque over moment of inertia. When you have a larger moment of inertia, you reduce the fraction, which means you reduce the angular acceleration. So you have a small angular acceleration, which means this thing literally accelerates slower than a different object that has a smaller moment of inertia. So a solid cylinder has a smaller, specifically half, it's half as large as a hollow cylinder. So it's got a twice as large acceleration. And then the rest of it is just basic kinematics. You know that an object with a larger acceleration is going to reach its target or its finish line the quickest. So anyway, I thought that was a really good demonstration. It kind of relates to what we just talked about last week, moments of inertia and rotational energies and a little bit of torque. So it's really good, sort of all-encompassing summary question. I do encourage students, while they're prepping for their midterm or your midterm coming up on Saturday, I encourage you to kind of go back and kind of really think about, get your hands dirty and see if you can kind of show this. it would be a good thing for you to practice. And obviously, in addition to doing textbook questions and the assignment questions. Okay, before we get started with the angular momentum lecture, I think I just want to briefly, because we are in the home stretch here, I think I briefly want to check in with you guys regarding the schedule. So here we are, we were on June, sorry. Here we are sitting on June, I think it's June 2nd today. No, it's not, it's June 1st today, sorry. Am I right? Oh no, it's not, it's June 8th. Don't listen to me, it's totally June 8th. So here we are sitting on June 8th, and that means your assignment 4 is due tonight. I don't quote me on this, but I think it's 7 p.m., but don't take that to the bank. Please just check online to make sure the due date is actually 7 p.m. Don't just take my word for it. It's whatever it says online. So the reason why I had to bump it, because originally I think we had it due on Sunday. The reason we had to bump it to Monday is because only today we're going to be covering angular momentum. And one of the problems on this assignment includes angular momentum. So most of your assignments should be done in theory. All of the other questions should have been doable immediately following last Wednesday's lecture on the 3rd. So you've had lots of time to do the other questions, so you shouldn't have to be rushing to finish all of the questions all in a few hours. The other ones have been done by now. And after today's lecture, you only have one question really left to tackle for the angular momentum question. And that should be more than enough time. I mean, that leaves you like 4 hours or something like that between this lecture and when it's due for you to do one question. So that should be more than enough time to attempt it. Okay, the other announcement I want to make is the use of CrowdMark. So our upcoming midterm is on the 13th, this Saturday. It's the same time as it always is. It's 8 a.m. to 10 a.m. Eastern Standard Time. I've inputted everybody's sort of timings. So for those of you who are out west, over in Alberta or British Columbia somewhere, I've obviously shifted your start time as I did in term test 1, because it is unreasonable to ask students over in BC to wake up at 5 a.m. To do a midterm. That is obviously not very fair to them. So if you're out west, your start time will have been shifted up. So you start at 8 a.m. your local time. I think over in Ontario, that would correspond to something like 11 a.m. or 12 a.m. depending exactly what province you live in. Whether it be Alberta or British Columbia. For everyone else who is east of Toronto or east of Ontario, starting later than 8 a.m., let's say you're in Europe and you're 6 hours ahead, starting later than 8 a.m. is obviously fine, right? It's just mid-afternoon for you and it's fine. And if you're over in Asia, 12 hours, so 8 a.m. would be 8 p.m. Again, it's not a perfect time, but it's not unreasonable. Like 8 a.m. is still, it's a reasonable, it's not like midnight or 1 a.m. Okay, now with CrowdMark, let me quickly pop over to the announcement section so you all can see it, as I forgot to log in. Okay, so you'll see here with the midterm 2 info announcement, we are using CrowdMark. Apparently CrowdMark is super expensive, and after it was announced that everything was going to be shifting online, we meaning the department, tried to find funding to purchase a CrowdMark license for our department, and it is, so I'm told, it's very expensive. So it took some time to sort of figure out how to do this and if it was worth it. And I know we've been using Canvas a lot for file submissions, and it's not perfect. I mean, it's a little bit cumbersome on your end. It's not terrible. I mean, it's pretty simple to upload an image, but I mean, it's still a little bit cumbersome. It was really cumbersome on our end when we're marking your tests, because it doesn't allow us the ability to annotate and circle and check mark and cross out and comment right on your test papers. So we were left having to make comments about your solutions kind of in a text box, and it's really hard to sort of use arrows and point to mistakes and explain why things are wrong when you can't annotate the image itself. CrowdMark is really nice in that it allows us to do that. So it provides better feedback for you. And I think it's also a nicer user interface for you guys as well. I think, you know, it's more flexible. It allows for, you know, slight accommodations. I mean, it allows you to upload late and then have me go in later and verify if things were only like 1 minute late, then it's okay. Canvas does not allow us to do that. Canvas, I have no ability in any way, shape, or form to upload your solutions for you. If you email me saying, Mark, I promise I was on time, here's an email of my solutions, I have no way to upload that with Canvas, zero. So there's no way for me to register that as part of your solution. There's no way to get that to the TA. So that's why with previous, like with the previous midterm, it had to be very strict, because there was no way for us to verify after the fact that, you know, it was part of your solution or any part of that. Canvas allows you to submit a little bit late, and I will have to go in after the fact, so and manually override them, but it at least allows you to upload. So if you are like a minute or two late, for one, let me be perfectly clear here, please do not push your limit. Please do not push your luck. Please do not be that one student who has to single themselves out by emailing me so I know who you are, that you're late. Please do not put yourself in that situation. I'm not advocating saying that that's a good idea. I'm just saying in a very extreme circumstance where something very unique happens and you are absolutely not able to upload your solutions in time and you're like 1 or 2 minutes late, at least CrowdMark has the ability for me to go in and say, yes, you know, 1 minute is fine. Now, again, I repeat, in general, 1 minute is not fine. There is no excuse for late submissions. I think at U of T, especially when we're doing in-person tests and the bell goes, you know, the professor in the room will say, everyone put your pencils down, and it's immediate. If we see anyone writing beyond that little dinger bell, someone will come and take your test away. That is normal procedure at U of T after an in-person test is completed. So please do not push your limit. Try your best, your absolute best, not to even go 4 seconds over, because that is equivalent to trying to write beyond the time limit. And, you know, it's not a very good situation to be in. However, CrowdMark is new, and I absolutely want to give everyone an equitable and fair chance at learning how to use CrowdMark. I said that in this announcement, I said that there was a sample assessment that I posted, and everyone should try to upload some sample solutions. You know, pretend as though it's midterm day and you needed to log into CrowdMark, so practice logging into CrowdMark. I want you to practice attempting the quote unquote sample midterm. I want you to upload the questions and push the boundaries. Pretend you have a 1-page solution and then upload it. Pretend you have a 2-page solution. Figure out, I want you to get your hands dirty with this in advance. Try to figure out how you would upload 2 images for 1 question. Let's say you need 2 pages for a solution. What if you realize halfway through the test that you made a mistake in your previously uploaded solution? Can you figure out how to go back and erase your old upload and re-upload a new one? I'll tell you now, there is definitely ways for you to do this, and it would be impossible for me to draft a document explaining all these ways. You just have to go and figure. It's pretty easy to do, to be completely honest with you, but you should not be learning how to do these things the day of the test. That's a waste of your time, and it's a stressful situation. So please use this sample assessment for testing file upload that I created on CrowdMark and push the limits of it and see if you can figure out how to use it properly. As of now, as of the date of recording this video, only 10 people have tried doing it out of a class of 150. I posted this announcement on the weekend, specifically June 5th. I think it was on Friday, actually. That worries me that we're using a totally new platform, and I informed students last Friday that we're using a totally new platform, and 3 days later, only 10 students have tried when the upcoming midterm is around the corner. That worries me. This is a warning. On the day of the midterm, any technical issues with CrowdMark will be invalid, because I am giving you ample opportunity to practice with CrowdMark. I've given you since Friday more than a week to practice with it. And if you don't choose to take advantage of this practice in advance, that's on you, not me. I'm trying to give you as much opportunity to practice as possible. The current deadline to practice on this assessment is Wednesday at midnight. And if there's a lot of people that practiced, and out of the people who practiced, if they email me, and if a lot of you email me saying like, look, the first one went well, but I want to make sure it's smooth on Saturday, could you create a second sample assessment to continue practicing? If there's enough of a demand for a second practice one, no problem, I'll make one. But if by Wednesday evening only 10 people have done practice uploads on CrowdMark, then you've had a good 5 days or more to practice, and hardly any of you would have taken advantage of it. So that doesn't really look good on you guys as a whole, right? So please take some time and practice file uploading, practice deleting something you uploaded and replacing it with something in case you find an error in one of your questions later on. Okay, the other thing I'd like to say before we jump into the lecture is that I've been receiving a lot of great questions over the weekend about assignment 4, which is due this evening. Far more questions, might I add, than I've ever had of any previous assignment. So I have my suspicions why I'm getting so many more questions now compared to before, but they're only suspicions. But I'm glad I'm getting them, because this means you're actually thinking about the problems. And it's good to be thinking. It's good to critically think and challenge what information is being presented to you. That's how you learn. I would like to address a main theme in the questions that I've been getting. I mean, there's some subtle differences that I won't get into, but a main theme is that, a lot of students are asking about approximations. Can we assume this is that? And, you don't mention friction. Do we need friction? You don't mention velocity. Do we need velocity? For one, when it comes to approximations, I'm not the keeper of approximations. It's not like if I say that an approximation is valid, then it magically is valid. I would love to have that kind of power. It would be amazing to be like, oh yeah, my $100 in my bank account is approximately equal to $1 million. That would be amazing. I would solve a lot of my problems, actually. But unfortunately, I do not have that power, nor does anyone have that power. When you make approximations, they're not perfect, obviously. They're an approximation by definition, but they have to be intuitively and logically correct. If I'm asserting to you that a lawnmower blade can be approximated by a disc, that's just demonstrably false. I mean, a lawnmower blade is a blade, not a disc. Now a lawnmower blade is a flat rod, right? A blade is flat, like a sword. So, if I want to say that a lawnmower blade can be approximated by a thin rod, I'd say that's a pretty reasonable assumption. If I wanted to say a lawnmower blade is approximated by a disc, that is not a reasonable assumption, right? Same thing with other parts, the other questions. If there's no value given in a problem and you think you need the value, unless there's a typo, which I'm verifying for you now, there's no typo. If I don't give you the value, you don't need the value, which either means when you introduce it, it'll eventually cancel, or it means you don't need it at all, and you're just approaching the question wrong. So I love the questions, keep them coming, like that's why I'm here. But in my responses to your questions, I'm not just gonna spoon feed you the answers. I'm gonna push back a little bit. I'm gonna sort of say like, well, why did you think this? Why do you think you need the speed? What made you think this? And then when you answer me, I'll say, okay, well, but do I actually give you the speed? Blah, 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 blah. Oh, I don't give you the speed. I wonder what that could possibly mean if I didn't give you the speed. Oh, that probably means you don't need the speed, right? So I'm trying to foster the sort of critical thinking, the sort of problem-solving nature, because that's how you actually become not just better at physics, but that's how you actually become a better thinker in whatever field you're in, right? You need to practice your critical thinking skills. So it's not that I'm not giving you the answers. It's that I'm trying to have you figure out the answers, and then that way you learn from the questions, okay? And I will always scaffold and point you in the right direction with my rebuttal questions. You know, I won't ask you a rebuttal question that's kind of out in left field that doesn't make any sense. You know, my rebuttal will always kind of bring you closer to the answer. I want to have you reach the answer without me spoon feeding you the answer. Okay, anyway, I think that is all of the administrative details I have. So without further ado, I think we can start the angular momentum lecture. Now, I've been doing a lot of talking. I planned for this. I knew we were going to be doing about 20 minutes of sort of administrative talking. So I'll give you a little bit of a break from my voice. And I want to show you a YouTube video to help motivate what we're about to study. And I will warn you now, it's going to blow your mind. Now, when I say blow your mind, you're not actually going to have your mind blown. If you're interested in science and you know, you kind of like explaining the world around you, this will absolutely blow your mind. Now, I understand a lot of students in this class are not here to learn physics. You're here because you have to be. So please bear with me, but this is still a really, really, really cool video.
I am here at the University of Sydney where the mechanical engineering shop has built this incredible piece of apparatus for me. It is a 40-pound, that is 19-kilogram flywheel on the end of a meter-long shaft. Can you imagine trying to hold this out horizontally with just one hand at this end? It is impossible, okay? Now I'm gonna let go. You gonna be able to hold this at all?
I hope so.
Can you lift it out? Make it horizontal. Hold it, hold it, hold it. Come on, just try to. I want you to hold it out horizontal. See if you can. Hold it, hold it. Oh, come on. No. What I'm going to do is I'm going to spin this up to a few thousand RPM, and then I'm going to attempt just that, to hold it from one end and have it out horizontally.
5, 4, 3, 2, 1. Boom.
I'm going to let go with my left hand. What you'll see is that the shaft remains horizontal. You can see it going around there.
It almost looks as though the wheel is weightless. How does this work? Well, instead of pulling the wheel down to the ground as you'd expect, the weight of the wheel creates a torque which pushes it around in a circle. You may recognize this as gyroscopic precession. For a more detailed explanation, click the annotation or the link in the description to see my video on the topic. Here, I want to try something more extreme.
I'm going to try to lift it over my head with one hand while it's spinning. Wish me luck.
But before I make the attempt, Rod wisely suggests that I first check if I can lift the wheel above my head without it spinning.
Let's prove that I can lift it just this end without it spinning. Here we go. I mean, it's just kind of awkward with the hand.
Careful. Careful.
Woo! Just barely. Oh, goodness. Do you even lift? Clearly I do not.
Undaunted by my lack of strength, I'm going for it. But I want to make sure that the wheel is spinning as fast as possible to give me the best chance of success.
Give it 10 more seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Go! That was perfect. Now I'm going to release my left hand and holding only with my right hand at the end of the shaft, I'll try to lift it up over my head. This is a 40-pound, 19-kilogram flywheel. Ready? Here we go. 3, 2, 1. Beautiful. Let's go again. In 3, 2, 1. Nice. Smooth. 3, 2, 1. It feels incredibly light as I do that.
Lifting it feels like.
Yeah.
Shouldn't.
I know. Honestly, I have lifted it up with one hand when it's not spinning.
Yeah.
And it feels really hard to lift it up. Like it's a big effort.
Yeah.
But with this, when it's spinning, it honestly felt like it was just
Wanting to go up by itself.
yes. It felt like I was struggling, like I was not putting in the amount of force that you think to lift that kind of weight?
I bet if you let it go, it'd crash down to the ground. That's not weightless.
We can't do that though. We can't do that part of the experiment. What we could maybe do is I could stand on a scale and we could see what the weight of me plus that apparatus does while I'm lifting it up over my head. See if I get lighter, in essence. You can see that just my weight is about 19 kilos. That's 91 kilograms. What do you think? You can make your prediction by clicking on one of the on-screen annotations, or if you're on mobile, you can click a link in the description. 5, 4, 3, 2, 1.
All right, welcome back. So that's a good sort of introduction of what we're going to talk about today. And angular momentum is the culmination of our rotational discussions. I started this rotational unit by saying we have to redo everything we've done since May. We have to redo kinematics, redo dynamics, redo energy, and redo momentum. Although instead of talking about all those four things in the translational sense, we have to talk about those things in the rotational sense. And up until now, it's been really fun. The presence of rotation has been challenging and new, and hopefully it grows your brain. And it really explains a lot of interesting phenomenon that we see around us. I mean, we saw that video before with Walter Lewin dropping those cylinders of different masses and different radii, and they hit the ground at the same time. And that's just very counterintuitive. So, I mean, our discussions of rotational motion are really critical in explaining the world around us. And once you know the physics, it's actually quite simple explanations for these very mystical looking things. Mystical in the sense that, you know, this guy was struggling to lift this really heavy object when it wasn't spinning. He was lifting it right at the fulcrum, like right at the heavy part. And then while it's spinning, he was able to hold it way, way, way far at the other end above his head with ease. That seems like magic. And yet, when you actually understand physics, it's actually quite a simple explanation. So that's what we're going to tackle today. And later on in the video, or later on in this lecture, we're actually going to see sort of a result of that. So moving on, here's the agenda for today. First, we're going to take some time to review some prior knowledge to make sure we have the right tools before we move forward, because this is actually quite an important topic, quite an important lecture. And then we're going to move on to actually introducing the notion of angular momentum, and then talk about the conservation of angular momentum and how it relates to the conservation of regular momentum that we're used to. And then we're going to do a little bit of a summary and then some examples for you. So here are the prerequisite skills that we need moving forward. We discussed, the very first thing we discussed was the linkage between translational motion, forward motion, and rotational motion. And the link is actually quite simple. The link comes from finding a relationship between our variables that define motion in the linear sense and variables that define motion in the angular sense. So our variables that define motion in the linear sense are d, v, and a, displacement, velocity, and acceleration. And the variables that describe angular motion is theta, omega, and alpha. Angular displacement, angular velocity, and angular acceleration. And there are three equations that kind of relate to these two quantities together. So that's these three right here. These are our linkages between the two realms, between the tangential and the rotational realm. This is what helps us with our analysis when we need to combine multiple themes together. Another rotational equivalent is moment of inertia, denoted by I. So I is the rotational equivalent of M. So we discussed that when we talked about torque. So please recall all of that, all of the information with that. And the last piece of prerequisite information we need to remember what the conservation of linear momentum is. And that's simply P total equals P total prime. And, you know, if you have a multi-object system, then that's just M1V1 plus M2V2 plus ... equals M1V1 prime plus M2V2 prime plus ... right? Just simple P total equals P total prime. So everything on this slide we are going to need moving forward. And so let's just jump at it. So we talked about in the previous, I think it was rotational energy. No, it wasn't. It was rotational kinematics is when we did this example. So we won't have to redo it because we've already done it. But just to remind everyone, the multiple choice question was Bonnie sits on the outer rim, Clyde sits halfway in, and if the whole merry-go-round is rotating with angular velocity omega, which one has, with Bonnie or Clyde, which one has the larger omega, the larger angular velocity? And if you recall our discussions, we're talking about solid body rotation. Solid body rotation is where all the particles in the object move together. The technical definition of solid body rotation is where all the particles in the object have the same omega. So by definition, the answer is Clyde has the same angular velocity as Bonnie. Here's a new one. It's a moment of inertia conceptual question. So we've studied moment of inertia last week, I believe. I think it was on Tuesday. So it's been about a week since we've done it. So I want to do a poll with you guys to see how much you remember before we move forward, because it's really important that we really truly understand moment of inertia, because it's a really important concept. So let me launch the poll here. There we go. Two spheres have the same radius and equal masses, meaning if you look at these objects just with your eyes, there's no way to tell the two of them apart. One object, however, is known to be a solid sphere of aluminum, and the other object is hollow. Which one has a larger moment of inertia? So we have 19, 20 out of 53, 24 out of 53, 26, so around half. $44 out of 53. Okay, I think we've kind of plateaued. I don't see the responses coming in as fast as they used to. So I'm going to end the poll here, and I'm going to share the results with you. So you can see here that the results are 11% for A, 24% for A, 60% for B, which is the Democratic winner, and 16% for C. So interestingly enough, a lot of you did vote for B, but there's definitely some spread in the answer. So let's kind of take a look at what's going on here. I'm going to hide the results so you can get your screen back. So here, this one asks, which one has a larger moment of inertia? Well, if you recall, moment of inertia is related to how far away the mass is located from the pivot point. So for a point mass, not like a sphere or a cylinder, just a point mass, all the mass is concentrated at one location. For a point mass, the moment of inertia is mr squared, meaning the farther the mass away, the farther the mass is away from the pivot point, the larger the moment of inertia, the harder it is to get that object rotating. So how does that translate to our sphere here? Well, if we have a sphere that's hollow, then all of the mass is concentrated along the perimeter. So if you rotate the sphere along this axis, all of the mass in this object is concentrated as far away from the pivot point or the axis of rotation as possible. So this moment of inertia, oh, and let me draw the other one, compared to the other one that is solid. Well, if it's solid and they have the same amount of mass as each other, then what happens is some of the mass is closer to the pivot point and some of the mass is farther from the pivot point. So here, the moment of inertia 2, I2, is actually less than I1 because much of the mass is closer to the pivot. Now, if you look, I believe they're probably about, well, I don't know for sure, but I know for a solid cylinder versus a hollow cylinder, they're twice one another. The hollow cylinder has a moment of inertia twice as large as a solid cylinder. And I think there's a similar pattern with spheres as well, although the exact ratio might be a little bit different than half. Close though. So the answer is the hollow one will have a larger moment of inertia, and that's because more of the mass is concentrated farther away from the pivot point. Okay, so we've done the prior knowledge. Let's just jump in, right? Let's jump right into angular momentum. What is angular momentum? Well, the definition of angular momentum is L equals I omega. And this shouldn't come as a shock to you. Well, maybe the letter L comes as a shock to you because, you know, for that silent L in, you know, angular. I know there's an L at the end of angular, but, you know, normally when we give things symbols, it's for the beginning of the name. I don't know, the silent L at the beginning of angular. I don't know where the L came from, probably some Latin-based name. But the formula should not come as a surprise to you. So the reason why we needed momentum as a prior prerequisite knowledge, as prior knowledge, is because momentum follows the same pattern we've been using up until this point. It's the same pattern we see with kinematics, with dynamics, with energy. Wherever we see the linear variable, we just swap it out for the rotational equivalent. So momentum becomes angular momentum, m becomes moment of inertia, I, and v becomes omega. So angular momentum is simply L equals I omega. Quite simple. So there's a slide that kind of shows that sort of comparison there. Now, here's where things get fun. There's a lot of similarities between linear momentum and angular momentum. In fact, most of it is identical. However, there's one small difference that actually opens up a whole new can of worms. So if you look here at the bottom of the slide, when I say the word momentum, or if anyone says the word momentum, inherently there's two different types of momentum they could be talking about. There's either linear momentum or angular momentum. Now the formulas for them are very similar, as we've seen. However, main difference, linear momentum is shape independent. The car, let's say there's Mark is driving a car of mass 1,000 kilograms and his speed is 100 kilometers per hour. What is his momentum? Dead easy. Mass times velocity will give you my momentum driving in that car. Nowhere did I say whether it was, you know, a sports car that was low to the ground, whether it was like a long bus, or if it was a short smart car that was like stumpy and kind of half of a car. Nowhere in there is the shape of the car a factor for the total linear momentum. It's shape independent. However, if something is rotating and I say, well, what's the angular momentum? The object has a mass of 10 kilograms and has an angular velocity of, I don't know, 4 radians per second. What's the angular momentum? There's actually no way to find out what the angular momentum is because it's shape dependent. It depends how those particles are oriented. Are they all clustered around the axis of rotation? Are they spread out? Or are they in some sort of oblong position like what we see here? This is oblong, meaning it's no nice shape. It's not a rectangle, it's not a triangle, it's not a circle, it's just kind of an oblong shape. And in real life, a lot of shapes are oblong. You know, like human bodies, for instance, are oblong. You know, we're not perfect cylinders or rectangles either, right? We're just sort of an in-between shape. So that's where the difference comes in with angular momentum compared to linear momentum. It's shape dependent. So all of our conversations are going to be talking about the implications of this shape dependency. Now, don't forget, linear momentum is a vector, so angular momentum is also a vector. And as with everything else rotational in this class, we measure the vector nature using our right-hand rule. So with linear momentum, it's dead easy. The vector nature of linear momentum is just the same direction as v. So if the velocity is to the right, then the momentum is to the right. You recall we have this construct of using our right-hand rule to determine the vector nature of these variables, quantities of motion. So for instance, we see the equation L equals I omega. Omega itself, omega, using your right-hand rule, you'll see omega has the vector nature up, using your right-hand rule, assuming the direction of rotation is indicated as such in this figure here. Now, looking at the mathematical equation, L equals I omega, I is a scalar. So mathematically, if you take a scalar and multiply it by vector omega, you're not changing the direction of omega, you're just changing the magnitude of omega. So that's what's happening here. Omega in this picture is the small little blue arrow pointing upwards, and L is the larger red arrow also pointing upwards, parallel to omega, but its length has been scaled by the scalar I. So that's what we see here. The length of the vector was scaled by scalar I. Okay, honestly, that's it. I could technically end the lecture right here and call it a day, because technically that's all the new information. It's honestly that simple in terms of new information. However, we obviously won't end the lecture this early because angular momentum is quite prolific and quite amazing. As you've seen with the opening video, it allows someone to hold a very, very heavy object over their head. And so far, you don't have all the puzzle pieces to figure out why. Technically, in terms of content knowledge, everything is now there. Technically, that one piece of equation I gave you, technically explains it. But we have no familiarity with this equation yet, other than its mathematical definition. So I do not blame you at all if you still have no idea why angular momentum explains why the object can be above his head in that video. So let's proceed. Conservation of angular momentum is nothing new. It's exactly the same as conservation of linear momentum. And it's actually using this principle of conservation of angular momentum that we will eventually be able to explain why he can hold this big mass above his head only while it's spinning. So, as we would expect with linear momentum, conservation of angular momentum just means the total amount of angular momentum before has to equal the total amount of angular momentum after. So some event can happen. I don't know what the event could be. It could be anything. Some event occurs, and the amount of angular momentum after must equal always the total amount of angular momentum before. Always. Now, please be careful. We are assuming an isolated system. Of course, if you're allowed to have external forces acting on your system, of course, you can change the total angular momentum of a system by acting with external forces. Of course, your car, your parents' car, your own car, I don't know if you own a car, your parents' car that's parked in the driveway, the wheels are not currently rotating. So the angular momentum of the wheels are zero, technically. However, when you're driving your car, the wheels are moving, and thus they will have angular momentum. But Mark, doesn't that violate the law of conservation of angular momentum? L total does not equal L total after. Well, it doesn't, because you're providing an external force on the tires, right? The force from the engine to get them moving. If you're providing work done in the system or on the system, and you put energy into the system using an external force, you will change the total energy of the system. So when we say conservation of either momentum or angular momentum, we assume that it's an isolated system, that nothing external is acting on it. And the way in which we achieve this is we grow our system just barely big enough to encompass everything that's operating. So if our system was only the tires of your parents' car, and we only took a camera and we only looked with tunnel vision at the tire, it would look like it violates the law of conservation of momentum, because the tires weren't moving and then now they are moving. However, if we expand our view to include not only the tire, but also the rest of the car, like the engine and the ground, then all of a sudden it makes sense. Now the wheels are rotating. Where did the angular momentum get stolen from? It got stolen from the engine, which, you know, is also provided by the ground because of the friction. So all you have to do is expand your definition of the system to be just barely big enough to include all the objects that are involved, and then all of a sudden, boom, conservation of momentum will make sense again. On a very grand scheme of things, with the universe, for instance, like you can't get bigger than zooming out than just looking at the whole universe. That's pretty much what we mean. Like overall, conservation of momentum has to be true in the universe, because if you include everything, then the conservation of angular momentum in everything has to be 0. So some things somewhere can spin one way, some things somewhere else can spin the opposite way. If you add them all up, they're going to get 0. Okay, what does that look like? Well, if you have L total equals L total prime, for a one object system, that would simply look like I naught omega naught equals I prime omega prime for one object. Now you might think to yourself, hey Mark, with linear momentum, how do you have conservation of momentum with one object? It's just m1v1 equals m1v1. Yes, the reason is because it is not shape dependent. So it's weird to look at conservation of linear momentum with one object. However, angular momentum is a function of shape. So if we had an object that could deform as it's moving, change its shape, change its orientation, not its mass, the mass stays constant, but the orientation of the mass might change. If that can change as an object is moving, then yes, you can say I naught omega naught equals I prime omega prime, because things will change. With multiple objects, same thing. We have I1 omega 1 equals I2 omega 2 plus dot 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 equals I1 prime omega 1 prime plus I2 prime omega 2 prime dot dot dot. It's the same parallel as what we discussed in our prerequisite skills for linear momentum with P total equals P total prime. So that's what the conservation of momentum equation the conservation of linear angular momentum equation physically looks like, right? It physically looks very similar to the linear counterpart. So let's do an example. Now, normally, if we were in person and, you know, I was able to teach with all of my equipment and you were sitting in front of me live in person, I would actually do this for you. And it's very fun to do because I get dizzy and, you know, it's you guys all laugh at me because I'm dizzy. And it actually really, really nicely shows what happens. Unfortunately, we're going to have to, you know, settle for someone else's video that they've made of this online. It's not as good as seeing it live, but it's better than not showing it at all. So this is also my bad attempt at Photoshop, by the way. There's my really badly Photoshopped head on someone else's picture. So let's read the premise of the problem and see if we can make heads or tails of it before we look at the video. Your physics teacher, me, hi, is holding an already spinning bicycle wheel. So the wheel's already spinning by the time I stand on this platform. Okay, I'm standing on a frictionless turntable. Of course, things aren't frictionless, perfectly frictionless. They can only be approximated to be frictionless. And in fairness, the turntable we have at UTM is fairly frictionless. It spins quite a lot for a small push. What will happen if Mark, who is currently holding the bike tire as shown in the image, what would happen if Mark flipped the bike tire over? So right now you see my arm, my left arm is on top and my right arm is on the bottom, right? What would happen if I flipped this? So my left arm, let me see if I can draw a really bad, hold on. Let me see if I can draw a really bad stick figure for you. So my left arm is now on the bottom and my right arm is on top. So, and it would flip. So if the initial direction of rotation is this way, then after I flip it, it would be the other way, obviously, because I'm flipping it. So if it was clockwise, then now it's counterclockwise. If it used to be clockwise, then now it's clockwise. So what would happen if I flipped it? If anything, maybe nothing would happen. If something does happen, what would happen? So that's the premise. I'm standing on a frictionless turntable, which means if there is any sort of recoil that happens, it would happen because there's no friction, so things would move. Now we just have to use physics to predict what will happen. So let's have a look at that video and see their explanation. I would love to do this in person for you. Unfortunately, I just can't, given the circumstances.
The tire the other way, then I'm going to flip the tire upside down. What should happen? Somebody said I should slow down, I should stop. Yeah, you think I should stop?
Slow down.
Slow down? Okay, let's see. You recording? Okay, wonderful. So I'm going to spin this way. So I want to spin the tire the opposite way. So here we go. Tire's spinning. And I'm going to start spinning this way. And I take my tire. What happened? I slowed down and stopped. What happened when I spun it back the same way? Stopped. Keep going. Whee! Now I want to look this way. Oh, I'm actually going the opposite direction now. And I flip it back upside down. Spinning. I just kind of hold it this way. Crazy. Should we see it again? Yeah. Let's see it again. All right, I'm spinning. Flip it upside down. I slow down. I had too much momentum going that way to start off with. Then I flip it upside down. Speed up. Slow back. What's going on? It's the Twilight Zone. Clearly it's the Twilight Zone.
Yeah.
Ooh, you can stop recording.
Okay, welcome back. So that isn't quite what I usually do with students. It's very close though. So you'll notice that this demo, he started himself rotating first. I don't know why he did that, but he started himself rotating first. And then when he flipped the tire upside down, he pretty much came to rest, pretty much. Now, our situation is a little bit different. I start off at rest, not moving, and then I flip the bike tire. So the demo here indicated it was the Twilight Zone, and quite frankly, a lot of cool little close-up magic, other than card tricks. Card tricks are just separate, but a lot of like fun little flashy magic tricks are actually just applied physics, just applied with a sort of sleight of hand and applied with a sort of showmanship. Most physicists are not showmen themselves. As you saw in this demonstration, he did not really exude confidence like Penn and Teller on stage. But nonetheless, there's a lot of cool, fun little magic tricks that are actually rooted in physics. So this would be kind of one of them. You could develop a magic trick like this. So let's use the conservation of angular momentum to kind of predict what would happen. So let's start with conservation of momentum, angular momentum. So momentum before, oh, I'm still writing in blue. Let me switch back to red. So momentum before has to equal momentum after. Well, what is my momentum before? Well, the total angular momentum before, there's only two objects in the system. There's me and the wheel. Just two objects, okay? Before, I did not rotate. Now, the guy in the video, yes, he did rotate. So he would have to include that, but we didn't. In this question, we did not rotate. So the angular momentum of Mark is 0. I'm not rotating. However, the wheel is rotating. We see in the image here that based on the direction of rotation of the tire, the angular momentum ahead of time is pointed upwards. You can verify this using your right-hand rule. Now, that means the total momentum, the total angular momentum before is in this green chalked right there. It's pointed upwards. So that means no matter what happens, I could throw the wheel away, whatever I want to do, whatever happens, the total angular momentum after has to be the same as what it started with. So this has to be true. I know that the answer after the equal sign has to be this exact amount of angular momentum upwards. It has to be. That's what the law of conservation of angular momentum says. Now, what are my objects? Well, there's again, there's myself, Mark, and then the wheel. We're not changing how many objects there are. Well, after the collision, it's not really a collision, but after the event, what do we know? We know that we flipped the tire upside down. So the new angular momentum of the wheel, L prime wheel, we know is pointed down. We know this because that's exactly what we designed for it to have happen. Well, you see here that if I don't include this term at all, if we ignore this term altogether, we see that the left side could not possibly equal the right-hand side. That the left-hand side has a net momentum beforehand pointed upwards, and the right-hand side has a momentum downwards. There's no way up could equal down. That tells me we're missing something. The law of conservation of angular momentum tells us we are missing something. The only other object that is in play here is Mark, is me. So that tells me, just by sheer mathematics, that tells me that I must take on an angular momentum such that when I add these two together, they give us the original. So that's how I get that the angular momentum of myself, Mark, is a large vector pointed upwards. More specifically, it's not just large, it's exactly twice as large as the initial angular momentum vector of the wheel. And the reason this is true is if you were to add vectors, tip to tail, then we know our total one has to sum to this green arrow here. Well, if I know the angular momentum of the tire after the collision or after the event is down, or negative L, then Mark has to be 2L, because 2L minus 1L equals L, which is what we started with, is just 1L. What does this tell us mathematically? Fine, it tells us I have an angular momentum after, fine. But what does this tell us in real life? The whole point of physics is that we can use it to explain the world around us. If I now have an angular momentum vector after the collision or after the event, it means I am spinning. So we see here that my angular momentum after the collision is going to have an upward vector. Using your right-hand rule, upward means, according to your right hand, I am going to be spinning in the original direction of the wheel. And that is exactly why when the man in the demonstration, I don't know why, he gave himself an initial rotation. I don't know why he did that. But if his initial rotation is up, and when he flips the tire upside down, then instead of inducing movement, he reduces movement. He works against his initial momentum. So he slowed down his rotation. And when he flipped it back up to the original location, he sped back up again. All of this is because of the conservation of angular momentum. It's a way to induce rotation in another object. That is the brilliance of conservation of angular momentum, is that you can actually induce things rotating, and it appears as if it's magic. Because at least when you talk about linear motion, you know, you talk about forces, things are pushing. You talk about a car colliding with another car in a collision, and you can, in your head, you can picture, oh yeah, the car is exerting a force on the other car. That's how it gets the other car moving. Here, there's no collision. Here, you're just flipping a bike tire. There's no collision. It's really difficult for your brain to sort of understand that simply flipping something will induce rotation. This is not intuitive. It's not, mathematically, it is perhaps intuitive. The math speaks for itself. It's fairly simple mathematics. But to actually grasp intuitively your gut instincts, what will happen in real life, none of this is intuitive. It is very unique and very, very not intuitive at all. Okay, here's another example. I've already said that angular momentum is shape dependent. Let's see what I mean by that. So here's a question. A man sits on a lab chair that is known to be rotating with an angular velocity of 1.2 revolutions per second. And he is holding weights in each hand. The moment of inertia of the system, let's say, is given to be 6 kilograms square meters. Don't forget the units, mr squared. So the units are going to be kilogram meters squared, right? Kilograms for the meters, r squared. Kilograms for the mass, and then meters squared for the r squared. If moving the weights closer to his body is known to decrease his moment of inertia, and this should make sense intuitively because you have mass that is far away from the axis of rotation, and you're bringing it closer to the axis of rotation, so you're reducing the moment of inertia, you're making it smaller because the weight is coming closer, you're reducing r. If moving the weights closer to his body decreases the moment of inertia to 2 kilogram square meters, what is the resulting angular velocity of the platform? Again, counterintuitive. Usually, I actually do this in class for you. I take an office chair and I spin in the office chair and I put my legs and my arms out and I pull my legs and my arms in, and you can see my speed change. Unfortunately, we can't do that at the moment, but hopefully we can get the gist of it here. It's very counterintuitive that anything even happens because there's no collision. I'm not throwing anything, you know, I'm just moving my body, and all of a sudden things happen. So let's see why things happen. Use conservation of angular momentum. L before equals L after. L total equals L total prime. Okay, so the before is when the weights are extended. After are when the weights are pulled inwards. Okay, so the angular momentum beforehand is simply I1 omega 1. Well, do we have those? Yes. I was given in the question. I was 6. The angular velocity was 1.2 revolutions per second. So we were given that. And then equals I2 omega 2. We're given I2. I2 is what? 2 kilograms square meters. And we don't have omega 2. So we were simply rearranging. You see here that omega 2 is I1 divided by I2 times the initial angular velocity, omega 1. We plug in our numbers, 6 over 2 times 1.2, so that's 3. 6 over 2 is 3, times 1.2, well, 1.2 times 3 is 3.6 revolutions per second. So you see here that we're not actually throwing the weights away, we're not making a collision, nobody is pushing us on a swing. You know, we are completely an isolated system, and all I've done is I have pulled the mass closer to the axis of rotation, and we see here that this is now larger than 1.2, meaning it got faster, which is incredible. If I was sitting in an office chair right now and I was spinning with my legs out and my arms out, and I pulled my arms and legs in, I would start spinning really, really fast. And it would look magical. It would look like I have a hidden wire somewhere, or like a hidden fan that was blowing me in a circle. That's not the case. It's just basic physics. You've actually seen, hopefully you've seen, this exact notion in figure skaters during the Olympics. I don't know if any of you watched the Olympics, but you know, when you figure skate, you see people twirl, and a big, glorious, apparently I'm not an expert in figure skating, but a really good move is when the figure skater starts themselves spinning, and they pull their arms in and they pull their legs in and they start spinning really, really fast, and they hold that fast spinning position for many seconds. And that's really hard to do because, you know, you're spinning, you're getting dizzy, it's hard to keep your balance, so it takes practice to sort of stay you know, vertical while you're spinning at such a fast speed for such a length of time. And then to pull out, you see the figure skater throw out their arms, and they stay balanced on one foot, but they throw their second foot out, and they make themselves really, really big, and then they slow down, and then that way they can safely come out of that spin. So hopefully you've seen an example of this happen, and that can be very easily explained using the law of conservation of angular momentum. Now, I want you to look, before we move on, I want you to look at the kinetic energies. If you look at the kinetic energies, let me change my color to black. The kinetic energy before the collision, or before pulling the weights in, is going to be 1/2 I omega squared. Well, that's going to be 1/2 6 times 1.2 squared joules. This is really going to be, what, 3 times 1.2 squared joules of energy. Well, the kinetic energy after is 1/2 I prime omega prime squared. So it's going to be 1/2, what was I prime, 2? And omega after is 3.6 squared. So this is going to equal 3.6 squared. Well, 3.6 is, well, 3.6 is bigger than 3. So 3.6 is bigger than, sorry, 3.6 squared is bigger than 3 squared. So we know that 3.6 squared is bigger than 9, and 3.6 is less than 4, and 4 squared is 16. So we know it's less than 16. So it's somewhere between 9 and 16. If we had a calculator, this wouldn't be a problem. I could just calculate it. But anyway, we know this is somewhere between 9 and 16 joules. But here, 1.2 squared is pretty close to 1. Definitely less than 2, right? Because the square root of 2 is 1.7 something. So here, this is going to be much less than 6 even, for instance. Let's assume 1.2 squared was 2, which it's not, but let's assume it's 2. Then 3 times 2 is 6. So the actual answer is much less than 6, whereas our answer is bigger than 9. Less than 16, but bigger than 9. So here you see that energy is not conserved. Momentum is conserved. L1 equals L2. But kinetic energy is not conserved, which means overall energy is not conserved. Oh, but Mark, doesn't that violate the law of conservation of energy? The law of conservation of energy says the energy within a system is conserved if no work is done on the system. So I could ask you, oh, let me circle it in red. I could ask you, we clearly see that there's more kinetic energy after the fact. What was the source of this added energy? Whatever the source was, it didn't change the momentum. Sorry, it didn't change the angular momentum. So where did that energy come from? I'll leave that for you to think about. Okay, we have now finished talking about the conservation of angular momentum. I've shown you 2 examples. One example is where we kept the shape of the object the same, where we induced rotation in the other object, right? That was me flipping the bicycle tire. That's where I remains constant, like moment of inertia, I remains constant. But, you know, a flipping or a change in one object will induce rotation in another object. I've also shown you a second example of the conservation of angular momentum where the same singular object can be deformed in mid-motion and induce changes of its own state, meaning it spins up, it speeds up, or it slows down. So it's very interesting. Now, we're getting very close to trying to explain, very, very close to explain why he was able to hold that thing above his head. It clearly has something to do with induced rotation. Okay, so there's my hint. It has something to do with induced rotation. We're getting there. We're going to build. We're going to keep building. But before we build, let's make sure we're solid on the foundations. So here's a bit of a summary. So the definition of angular momentum, just mathematically, is L equals I omega. Quite simple, very analogous to linear momentum. The vector nature, or the direction of L, is very simply determined by the right-hand rule. It has a conservation law, just like angular momentum. And it's only valid when there's no net external torques, meaning there's no forces acting on the system, no net forces acting on the system. And it is shape dependent. L is shape dependent, which is different than its linear counterpart. And it has a very, very interesting, hidden, non-intuitive ability to induce rotation. Okay, so let's do some examples. We'll start with a medium one. I need to make some space. Give me a second. Okay. A person of mass 75 kilograms stands at the center of a rotating merry-go-round platform. Okay. And the radius of the platform is 3 meters. All right. All right. And the moment of inertia of the merry-go-round is known to be 820 kilogram meter squared. So the moment of inertia of the merry-go-round is 820 kilogram square meters. Okay. The platform rotates without friction with a known angular velocity of 0.95, oh boy, radians per second. The person walks radially. Radially means along the red line that I've drawn, along to the edge of the platform, meaning to the perimeter or to the circumference of the merry-go-round platform. Calculate the angular velocity when the person reaches the edge. So calculate omega prime, and B, the rotational kinetic energy before, oops, and after. Okay, so we now have the diagram, we have the list of unknowns, and we have the list of givens. Let's have at it. Given what we're asked for and given what we need, with a bit of practice, it should be fairly obvious that we need to use the law of conservation of momentum. Now, it's especially obvious presently because we're in the middle of that lecture. So L total equals L total prime. So this is going to be the angular momentum of the person plus the angular momentum of the merry-go-round equals the angular momentum of the person prime plus the angular momentum of the merry-go-round prime. So same setup that we've always done with regular momentum. It's fairly straightforward. So the angular momentum of the person ahead of time is 0 because they're standing at the center of the rotating object. So if they're standing at the center of the rotating object, they don't have any sort of speed. They're not rotating at all because they're at the center. Now, technically, of course, something can't be like a human body can't all be concentrated at the exact center. Of course, that can't be true. So this is a little bit of an approximation, but we're assuming that they're at the very center, so there is no rotation. But we do know what the angular momentum of the merry-go-round is in advance. It's going to be I omega 1. Or I didn't say omega 1, I just said omega, didn't I? Okay, now after, there's a time delay. The man is walking along the radial cut, you know, so there's a bunch of things happening in the middle. We don't care what happens in the middle. We just care about before and after. Before meaning at the center, after meaning at the edge. So eventually, they will end up here at the perimeter. And what are going to be our variables at this point in time? Well, it's going to be the the moment of inertia of the person at the end times omega prime plus the moment of inertia of the merry-go-round times omega prime. Now, the moment of inertia of the merry-go-round doesn't change. Merry-go-round is still the same shape it was after as it was before. Okay, but the person's moment of inertia has changed because the person is now a larger radius away. So here, do we have the radius? Yeah, it's 3 meters. Okay, so this, the angular momentum, the moment of inertia of the person is the person is a point mass, right? He's not a disk, he's not a cylinder, you know, he's not a sphere. It's a point mass standing along the perimeter. So a point mass, the moment of inertia is given by mr squared plus the moment of inertia of the merry-go-round. Factor that out, times omega prime. This equals omega I omega. So this means omega prime is going to be given by I omega divided by mr squared plus I. And if we plug in all of our values, we're going to get 820 times 0.95 all over. The mass of the person is 75 kilograms. So 75 times, what's the radius? 3. So 3 squared is 9. Plus the moment of inertia of the merry-go-round is 820. So there you go. You plug everything in and you can approximate your, well, you could actually calculate your answer if you had a calculator. I don't have a calculator, so let's do some approximating just to continue to show you how you might approximate. So 820 could be around, let's say 800. 0.95, come on, let's just call that 1. 75 times 9. Well, I don't really want to deal with 75 times 9. So, you know, you could round those. Now, I guess 75 times 9 is not terribly hard, but, you know, 75 times 10 is relatively easy. So that would be 750. It's approximated, right? We're doing approximations, plus 820. So this is going to be around 800 over, so let's see here, 8 and 7 is 15. So this is going to be around 1600, I guess. So this is going to be around a half. It's going to be around a half, approximately. I don't know what the actual answer is, but it's going to be around a half. And that's 0.5 radians per second. Now, if you think about this intuitively, just to make sure we did the question right, overall, we are increasing the moment of inertia of the system. The person starts off at the center and then walks outwards. So that's like the figure skater who is spinning really fast. It's like the figure skater pushing out their arms and pushing out their legs. The figure skater is increasing their moment of inertia, thus slowing down their angular velocity, slowing down their rotation. So here, when the person is kind of walking up toward the perimeter, they're doing just that. They're increasing the moment of inertia of the entire system, Thus, in theory, it makes sense that the resulting angular velocity is lower than what it started with. So my sanity check tells me we did something correct. Now, part B says to calculate the rotational energy before and after. I already did that before in the previous question. It's fairly straightforward to do. It's 1/2 I omega squared. So that would be 1/2 times 820 times 0.95 squared. And then this one would be 1/2. It's the sum of two rotational energies, actually. It's E rotational from the person plus E rotational from the merry-go-round. So this is going to be 1/2 I of the person omega prime plus 1/2 I of the merry-go-round omega prime. And I'm forgetting my squareds. Of course I'm forgetting my squareds. So then you can just plug in your values and get your numbers. If you actually cared, if this was an actual quiz or a midterm or something, you would probably need to follow through with that. But there's the setup for you. So for the interest of time, I don't want to calculate the numbers. Okay, here's another thought experiment for you. Here we have a car that is traveling along the flat road. And for some strange reason, I don't know, to go with it, let's say there's a vertical loop-the-loop in the middle of the road. I don't know why there would be, but let's just pretend there is. So the car goes in here and then travels around the loop-loop and then comes back out. Well, here, it looks like the angular momentum before does not equal the angular momentum after. Here, when the car is going on flat land, it's flat. It's not traveling. It's not rotating. It's just translational motion. The car's moving forward. So the angular momentum ahead of time is 0. In advance before 0. However, during the loop, let's say halfway up at the very, very, very top of the loop, the angular momentum, the car's in the middle is traveling uniform circular motion. So there is, in some sense, not even some sense, in all of the sense, you have a mass that is a certain radius r away from a pivot point that is rotating. So there is going to be a non-zero angular momentum. This seemingly violates the law of conservation of angular momentum. This seemingly violates that L1 equals L2. Because there's no way that 0 equals something that's not 0. Like 1, for instance. So what's going on here? Is there actually a violation? Well, of course not. You should be very skeptical when there's such strong language, like on the test or something, if you see a question like, does this violate the conservation? No. You know, as soon as you hear the word violate, the answer is probably no, it doesn't. There's probably a good explanation. So if you're finding yourself saying, yes, it does violate it, you're doing it wrong. Psychologically speaking, you use some psychology in the problem, you're doing it wrong. What is actually going on here? What's actually going on here is you have to remember the conservation of momentum, either linear or angular, is only true in an isolated system when there's no other forces acting on the object. If your view is only the car, and only the car, you tunnel vision only on the car, then I agree with you, this seems to violate the law of conservation of momentum. Seems to, not actually, just seems to. However, we're forgetting that the system is also including the road, because that's touching the object. So if you zoom out and you include the road in your system, you see that the road is actually applying a normal force on the car. And it's the normal force from the road on the car that is responsible for this uniform circular motion, and thus responsible for generating this angular momentum. So there's an external force acting on the car. That is why the car is able to have its angular momentum changed. In the same way that when your car is parked in the driveway, the wheels aren't moving. But when you turn the car on and you drive it, your wheels start moving. There's an external force acting on the object. Therefore, you can not only change its linear momentum, you can also change its angular momentum. So here are some examples of angular momentum that you might see and that you might not see, but still affect your day-to-day lives. Now, for those of you who are brave and go off the diving board, when you jump off the diving board, you can tuck yourself, you can pull in your legs, pull in your arms, and you can start tumbling and doing a somersault off the diving board. But you don't want to hit the water tumbling. That would probably be not very safe. So what your brain intuitively does is it stretches out. So right before you hit the water, you stretch out again, your legs stretch out, your arms stretch out. And what that's doing is it's slowing your angular acceleration again. So it's not that you've stopped tumbling, it's that your angular velocity is so slow that you can safely hit the water pretty much in a straight line, pretty much. We've already talked about the figure skater example. Now, one example we haven't talked about is planetary motion. For those of you who don't know, orbits are actually ellipses, and a circle is a special kind of ellipse where the major and minor axes are actually equal to each other. However, most planets don't follow a circular orbit. Now, Earth is unique in many ways. Not only is it the perfect distance away from the sun to support a normal temperature for life and plants and humans, it's actually one of the only planets that has nearly a perfectly circular orbit. That doesn't violate any physics because a circle is a special case of an ellipse. But in general, planets have elliptical orbits, and it's well documented that when a planet, this green dot here, whips around when it's close, it travels faster. It whips around really fast. So, obviously when the planet is closer to the sun, in this example, it would be warmer because it's closer to the sun, right? So it would actually not be warm for very long because it would whip around the sun quite quickly. And then when it's far, 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 far away, it actually travels slower. And thus it would be colder longer over there with an elliptical orbit. And this can be explained, the sort of slow nature traveling far away versus the fast nature over when it's closer, that can also be explained using conservation of momentum with I1 omega 1 equals I2 omega 2. When the planet is actually closer to the sun, its moment of inertia, it's pivoting around the sun. Right? The sun is the center, well, not the center, it's one of the foci of the ellipses, but it's the center of rotation or the pivot point. So when it's closer to the sun, it's closer to the pivot, which means it has a lower moment of inertia. But when it's farther from the sun, it's farther away, which means it has a larger radius and has a larger moment of inertia. So as if I goes down, omega goes up. So when the planet gets closer to the sun, I goes down, so omega has to go up to compensate. Another thing that you see, well, not that you see, another thing that we experience in our day-to-day weather resulting from conservation of angular momentum is a lot of air circulation. So like, for instance, our whole Earth is spinning, right? So if you have a column of air, you just take a slice of air from the surface all the way to all the way to space. If you just take a column of air, that column of air inherently has some angular momentum because it's part of the Earth that's spinning in a circle. Now, when you push this air over topography, like over a hill or more specifically a mountain, if you push it over a mountain, then what you're doing is you're changing the radius away from the center of rotation. So if you have the Earth here, for instance, and you had a mountain, here's a mountain, here's the axis of rotation, and if you had a column of air, let me change my color here for a second, if you had a column of air down near the Earth's surface, here's my column of air, then as that air gets pushed over the mountain, you're raising the air column, right? So the air column is now farther away from the axis of rotation. So you're changing its moment of inertia, which means you're going to be changing the speed of the air column. So when air converges meaning like comes together, it speeds up, and when air diverges, it'll slow down. And that's a result of changing its moment of inertia relative to the Earth's rotation. So we actually get these really fun and interesting weather patterns in and around topography, like mountains. Mountains will take advantage of the conservation of angular momentum, and it'll actually induce waves in our atmosphere. And they're actually called Rossby waves. I don't want to Google it, but if you've heard of the jet stream, if you're from Canada or Southern Ontario, or even Europe, actually, anywhere in the Northern Hemisphere, you will have heard of the jet stream. The jet stream is like a wave in our atmosphere that's actually induced by the conservation of angular momentum and forced by our topography. So that's just really cool to me. There's a lot of things in our day-to-day life that are just explained by the conservation of angular momentum. It's actually quite amazing. Now here, I put a picture of a motorcycle and a guy turning a motorcycle. Now, obviously, if the motorcycle wasn't moving and someone tried to turn a motorbike like this, they would literally just fall over. However, a motorcycle or pedal bike, the same principles apply. When you turn on a bicycle, you lean, but you don't fall over. You lean into the turn, and when you're done turning, you lean back. So you're now perpendicular to the ground again. How does this work? How don't you fall over? That's really what I'm asking you here. Why don't I fall over when I am on a bike and I try to turn? So in order to answer this question, by the way, we are getting incrementally closer to explaining why in that video, the guy was able to hold the thing above his head. I've already given you the hint that it's something induced, and we're getting a little bit closer and a little bit closer and a little bit closer. So bear with me, we are getting there. First, let's answer why don't I fall? So in order to say why don't I fall, we first have to watch another video. And again, I would show you a live demonstration in class, but we don't have that luxury. So unfortunately, the best we can do is settle for these videos. So let's take a break from me talking for a second, and let me share my screen and let's watch this video.
Physics, at its most basic, is just a description of the motion of the stuff in our universe. This planet goes this way, that rocket goes that way. Except that some, in they move without going anywhere. I'm talking objects that spin, revolve, rotate, pirouette, orbit, circle, gyrate, whirl, twirl, cartwheel, and so on, like a planet around a star, an electron in an atom, or even our solar system going around the gravitational center of the Milky Way. From up close, they're certainly moving, but in the grand scheme of things, that motion doesn't take them anywhere. We can still talk about it though. Just like momentum is a concept that describes how much oomph an object has when it moves in a straight line, angular momentum is a way to account for how much oomph objects have when they're going in circles, figuratively or literally. And angular momentum is simple in theory. Pick a point, any point. Pretend your object is moving in a circle around that point. Figure out how fast the object is moving along the circle, never mind that it probably isn't moving exactly along the circle and that the circle might have to change size over time to follow the object. But anyway, then multiply that speed times the size of the circle and the object's mass. And there you have it, angular momentum. For example, a 2 kilogram, 60 centimeter diameter bicycle wheel going 20 kilometers per hour would have an angular momentum of about 7 kilogram meters squared per second. Is that useful to know? The reason we care about angular momentum is that if you take a bunch of objects that are interacting electromagnetically or gravitationally or whatever, and add up all of their angular momenta into one number, then that total value won't change over time, unless some other objects from outside come in and mess things up. So as another example, the Earth, which is 150 million kilometers from the Sun, orbits at 30 kilometers per second and has a mass of 6 times 10 to the 24th kilograms, has an angular momentum of 2.7 times 10 to the 40th kilogram meters squared per second. That's 4,000 quintillion bicycle wheels. And this angular momentum stays roughly constant over the course of the Earth's orbit, year in and year out. But what's amazing is that even if the Sun and the rest of the solar system were to suddenly disappear, the Earth would still have that same angular momentum about the point where the Sun was. Without the Sun's gravity, the Earth would of course now move in a straight line, requiring an ever larger imaginary circle as it got farther from the point where the Sun used to be. But as the Earth continued through space, its 30 km per second velocity would also point less and less along the circle, so when you calculated the angular momentum, the decrease in velocity would exactly cancel out the increase in the size of the circle, and you'd always get the same answer, 2.7 times 10 to the 40th kilogram meters squared per second. So even when nothing is rotating at all, angular momentum is still conserved. And that's the beauty of a law of physics. It works, even when you try to break it. This video is brought to you in part by Audible.com, the leading provider of audiobooks across all types of literature.
Okay, welcome back. So that was a very quick video, and the gist of the video said that there's always angular momentum, even when things aren't rotating. And it's really hard to wrap your head around that idea that there's always angular momentum, even though things aren't rotating. And the gist was, or the explanation was, you can think of the object having been rotating around a fixed point, and as the object is going in a straight line, the radius of the circle just keeps getting bigger and bigger and bigger. But as the radius gets bigger, the direction that the tangential velocity is pointing in the direction of the circle gets less and less and less. So even when things aren't rotating, things still have angular momentum, which is super weird and super cool, and a lot of other situations that we were not previously able to do. So to show you that, let me show you an example. I first have to insert some space because we are going to need some space for this. So here's an example of what I mean when I say an object has angular momentum even when it's not rotating. So in this figure here, we have a small 50-gram mass that slides down a frictionless ramp through a height difference of 20 centimeters. And then hits a uniform rod of mass, 100 grams, and a certain length of 40 centimeters. The rod then pivots around the origin through angle theta before momentarily coming to rest. Find theta. Now, finding theta is neither here nor there. I will try to set it up for you. The important part is I want to show you guys how to analyze this problem. And the trick is needing to know that even though things aren't rotating, they are rotating, which is kind of weird. So let me show you what I mean by that. First off, we have to analyze the first part. The first part is the object falling along the ramp. This is fairly easy to do. We say that the speed, well, we say that the energy before will equal the energy after. Ahead of time is mgh, after is 1/2 mv squared. So that means the speed at the bottom of the ramp is going to be √2gh. That was fairly easy. That was back from energy. We've done that a long time ago. So we now know the speed that this object is going at the bottom of the ramp. That's fairly easy. Now, this rod, this heavy rod, 100-gram rod, is just hanging from a pivot point vertically straight downwards. And this block comes in and messes things up. This block comes in and strikes the edge of the rod. And they stick together. I don't know, maybe the rod is sticky, or maybe the object is sticky, I don't know. But they stick together, and then the whole thing, after the collision, the whole thing moves as one unit and swings upwards. How far up does it swing? Well, in some sense, I mean, there's absolutely a collision here. So momentum should be screaming at you, right? Because collisions and momentum are synonymous. Now, what kind of momentum? You might be very tempted to use linear momentum because it's the collision and we've seen that kind of thing before. However, the issue is it rotates. As soon as it collides, it does not move forward. It rotates forward. So you can't use linear momentum. You have to use angular momentum. So here's the trick. Right before, just a fraction of a second before the collision, we assume the object is actually rotating about the pivot O. That's a terrible straight line. It was supposed to be a straight line, my apologies. But we assume the object, it's not even an assumption, it's true, as you saw in the video I just showed you, that even though the green block is moving straight, you can think of a change of a frame of reference will tell you this. You can say that, you know, the object is moving momentarily in uniform circular motion around the pivot with this radius, with that radius. And that's how you do the question. You say L before, or I'll just say L. L equals L prime, where we say we have the L of the rod plus the L of the mass equals L of the rod prime plus L of the mass prime. And the L of the rod, this rod is initially not rotating. It's not moving forward, it's not rotating forward, it's just not moving at all. However, the angular momentum of the mass, or the rock, or whatever it's called, is non-zero. We say that it's going to be I omega. And this equals, and they stick together eventually. So this is going to be I omega prime plus, or I rod omega prime plus I mass omega prime. So this is us setting up the conservation of angular momentum equation. Now, what is the moment of inertia of this mass? Well, it's a point mass. All of the mass is concentrated at the very edge of the rotation. So it's going to be mr squared. And omega, we don't know omega. We know the speed. So let's see if we can represent speed in terms of omega, or omega in terms of speed. So we know v over r is equal to omega. And the moment of inertia of a rod, well, if you look back at our table, we don't actually have the moment of inertia of a rod spinning around this pivot. We have the moment of inertia of a rod spinning around the middle. So we can use the parallel axis theorem. We see that this is going to be the moment of inertia of a rod plus the distance between the center of mass and the new pivot, plus the moment of inertia of the mass, which we know is already mr squared, all times omega prime. So I just factored out the omega prime there. And overall, I believe this works out mathematically to 1/3 mass of the rod, oh boy, mass of the rod, length of the rod squared, plus little m. Now r is going to be the length of the rod squared, omega prime. And this is going to equal mrv. And I think we have everything now. Omega prime is going to equal mrv over 1, well, I can factor out the L, I suppose. Or I guess this R is L. So this is going to be L squared times 1/3 mass of the rod plus mass of the block. And cancel, cancel. So we're going to get, what is this? mv over L times 1/3, not 1/2, 1/3 mass of the rod plus mass. There you go. So that's going to be the rotational, or the angular velocity after the collision. And we can obtain that using, using conservation of angular momentum. There's a little bit more to the question. The reason why this is a 3-star question is because we now have to take this information and use conservation of energy again to figure out how far up it will swing. For the point of this video, for the point of this lecture, I'm not concerned with showing that. That practice can come later on when you're doing your own homework or later on in tutorials. So, why don't I fall? Well, let's look at one other video, and I know we're kind of coming up at the end of the lecture here, but let's look at one other video. Let's look at one other video very quickly.
The wheel is spinning and it still weighs 91 kilograms. You've made your prediction. Let's see what happens when I throw it up over my head. In 3, 2, 1. What do you think?
I don't know about you, but to me it looked like a shaky mess. Let's watch that again in slow-mo and I will graph the scale readings. As you can see, during the lift, the scale oscillates around 91 kilograms, the same as it read when I was stationary, so it seems the apparatus doesn't get heavier or lighter when it is lifted while spinning. The only large deviation from the average comes at the end of the lift, when I let the wheel fall so the scale reading drops, and then I slow its descent and so the scale reading rises. So the question remains, if the wheel doesn't get lighter, why does it feel lighter? This demonstration was first performed by Professor Eric Laithwaite. Listen to how he describes it.
So here goes 40 pounds of wheel as light as a feather. This is not a conjuring trick, this is a fact of science.
He sure makes it look easy, doesn't he?
Watch it again carefully. A fact about a spinning wheel that so far everyone has missed.
Professor Laithwaite claimed the gyroscope's properties couldn't be fully explained by Newton's laws of motion. I disagree. But in order to understand why the wheel feels so light, we first have to consider why it feels heavy when it's not spinning.
So two-handed, that's as far down the shaft as you can hold it?
Yep. Holding the shaft horizontally, you clearly need to provide an upward force equal to the downward weight of the wheel. But this is not enough, because with only these two forces, there would be a net torque causing the apparatus to rotate. So you need to create a counter torque in addition to supporting the weight of the wheel. This requires pushing down with one hand and pulling up with the other. And the upward force must be greater than the downward force by an amount equal to the weight of the wheel. So the force on each of your hands is significantly greater than the weight of the wheel. Now once the wheel is spinning, the torque due to its weight now causes it to precess rather than fall to the ground. Therefore no counter torque is necessary. You only need to supply an upward force equal to the wheel's weight, so it feels lighter. Now the trick to lifting the wheel over your head is to push it forwards as you release it. Laithwaite knew this. If you force a gyroscope to precess faster, it lifts up.
Hurry the precession and it rises.
But the weight doesn't change.
Similarly, if you slow the precession of a gyroscope, it goes down.
Slow the precession and it falls dramatically.
I'll show it to you, Rod.
Now show it to me.
It's hard to go back to the way that it doesn't want to process.
With 2 hands. So you can't say it becomes as light as a feather when it's rising.
It certainly doesn't become as light as a feather. I can say that too from having felt it. But it does feel lighter. And I think maybe part of that has to do with the fact that I'm not having to counter the torque with my hand. You know, all I have to do is support the weight of the disc, but I don't need to provide any torque with my hand to counter that gravitational torque,
Yeah,
which is what makes it feel so awkward when you're trying to hold it when it's static.
When you apply a torque, as you were, then there's a force up on one side of the hand and down on the other side. And if you decrease the force on both sides, then it will actually feel lighter.
It feels lighter without actually getting lighter.
Yeah. What it does is to decrease the apparent weight that you're feeling.
Okay, so welcome back. There's finally our answer, is that when the wheel is spinning, it wants to drop, but because of conservation of angular momentum, when it wants to drop, there's a counter torque or a counter angular momentum induced upwards, and it helps bring that thing upwards. And what the older gentleman was saying at the end there was, when it's stationary and you're holding it in your hands, not only are you having to support the weight of the really heavy object, but you're also having to support the counter torque. So you're on one side of your hand, it's really heavy. On the other side, it's really heavy, but in opposite directions. And while the wheel is spinning, because of the induced angular momentum kicking it back up, it reduces the sort of extra heavy feel on one side and the extra heavy feel on the other side, meaning your hand overall is feeling less apparent force. Even though it's still supporting the same amount of mass, it's less apparent force. So that brings us to our last topic, and I know it's 3 o'clock, so bear with me just a little bit. Our last topic is called precession. And precession is really interesting, and it's exactly what you just saw. So picture this. Picture a bicycle tire, or that big object we just saw on the end of a rod. This could be someone holding the rod right at the end, and this is that really heavy object spinning. You've seen the phenomenon where it can be held with one hand at the end of the rod and the rod does not fall. Seemingly impossible. Here's why. Here's the pivot point, because that's where we're physically holding it. If the wheel is rotating as shown, then of course, gravity is going to be pulling down. So you can actually calculate this torque due to gravity. It's mg. We know the lever arm is L, so we know the torque due to gravity is mgl. Now, because there's a torque, then the angular momentum vector that used to be pointing horizontally, remember, use your right hand, grab the wheel, fingernails in the direction of rotation, your thumb will point in the direction of the angular momentum. So the angular momentum used to be pointing horizontally. But when gravity pulls it down a little bit, then the angular momentum vector will now point a little bit angled downwards. Down here, it might be better if we use this over here. So it used to be traveling horizontally, or the angular momentum vector used to be horizontal. Now, the angular momentum vector prime is pointed down because gravity is in the middle of pulling it down. Now, that means there's a change in angular momentum. But momentum is always conserved. Angular momentum is also always conserved. So if there's a change in angular momentum of one object, there has to be an induced angular momentum in something else. So here, what we see is that because momentum is conserved, we get the sort of induced angular momentum upwards. And where does that angular momentum act? Well, this tire or this wheel is rotating like this and spinning and spinning and spinning and spinning and spinning. But the induced angular momentum is a counter torque acting at this pivot point upwards. And you can prove this using your right hand rule, right? If you know there's an angular momentum upwards, point your thumb upwards and then rotate your fingernails in the direction of the induced angular velocity. So using your right hand rule, if this induced angular momentum right here upwards is going to induce, I got it here. It's going to induce a speed backwards, right? Thumb in the direction of the induced angular momentum, delta L prime, according to the slide, and then your fingernails are going to rotate in the direction of the induced velocity. So this whole bicycle tire is physically rotating backwards, but the whole thing here is actually going to rotate in the opposite direction. This is what is called as precession. And the precession is caused by gravity pulling down on this bicycle tire. and inducing an angular momentum upwards to keep it afloat or to keep it level, but it can't do that for free. It steals that angular momentum to keep it raised. It steals it by rotating in the opposite direction, and that is what precession is. The same prof that we saw earlier, Walter Levin, he has a similar construct demo. And I know we're a little bit over, we're 3 minutes over, but please bear with me. We have a really nice video from him. And if you're kind of confused about how all that happened, because it happened really fast, let's watch that video, and hopefully his explanation and him doing it recorded, makes more sense to you. So it's our one last video. Please bear with me. It's our one last video.
Suppose I have here a string, a rope, like we have there. And I stick into that rope, I attach to the rope this wheel, just like so. And I let it go. Well, we all know it will happen. Clunk. It's clear. All right. But now I'm going to spin it before I let it go. Where's the wheel? The wheel is here. So we'll spin it up, and then we'll put it in here. Notice the way I'm spinning it. I'm holding it away from you now. I'm going to change it and do it differently next. And there it goes. About 10 seconds. Isn't that amazing? And it rotates seen from below clockwise. Now it's going this way, and I'm going to redo the experiment, changing the direction of rotation, and then it will go the other way around. And now the angular momentum, is it rotating like this, is pointing here. Spin angular momentum is pointing like this. Torque is like this. And so the spin angular momentum is chasing that torque. I'm the spin angular momentum, I'm the torque. This is the torque. It's chasing it. All right, so I had this in my right hand. That's all right. And now I will, so when I spin it up, let it first go around, which was roughly 10 seconds, what we calculated. And now I'm going to put 2 kilograms here at the end. And then you will see an instantaneous increase in the precession frequency. You see, it goes much faster now. I take it off, and then it goes back to its roughly 10 seconds. So what I have done is, I have increased this torque, but not at the expense of M. Because the reason why the M cancels is because the moment of inertia has an M in it. But if I just hang this object on it, that doesn't change the moment of inertia of the spinning wheel. None of this is intuitive. None of this is intuitive. None of this is intuitive.
Okay, so I hope that makes a little bit more sense. I know it's all very new to you. Really, it all boils down to conservation of angular momentum, where L equals I omega. It's a very simple equation, but very, very powerful. It governs so many things. Technically, linear momentum, as we learned today, linear momentum is actually a subset of angular momentum. We learned today that even when an object is traveling in a straight line, you can think of it as rotating along a very, very, very large circle with a close to an infinite radius. So everything we learned about linear momentum is still true, but it's technically a very specific niche situation of angular momentum. So everything, you saw how many things were explained by linear momentum. So many more things are explained by angular momentum. Honestly, angular momentum is by far my most favorite chapter in 136 because it explains so much of the world around us. And I actually only got into physics versus the other scientific disciplines because physics is really the only discipline that just digs its hands really deep into the world and trying to figure out really why do the things around us happen the way they do. And angular momentum for me is in my eyes the thing that just bam, it just explains so much. It explains linear momentum. Linear momentum is related to forces. The derivative of momentum is obviously a force. We looked at that. What's a net force? And the forces are related to kinematic motion and energy, and rotational motion is related to those translational things. So like angular momentum is really the at the top of everything here. It's the top of the hierarchy. It explains everything. It connects everything beneath it. It's rotational, so we know how to relate rotational and linear. It's momentum, so it explains everything collision related. And collisions are related to forces, which is related to torque. It's just, I don't know, it's a beautiful, beautiful topic. And I really do hope you guys can take some time and go back and just really dig deep into doing some of these homework problems because they're so cool. You can look at these videos here. I know the link is not very Googleable, but if you Google like Walter Levin, spelled with a W, but I think it's German, so you don't pronounce the W. Walter Levin bike tire, for instance. I'm sure that video will come up. So it's so cool, and I really do hope you get to do some sort of hands-on work on your own. Okay, in terms of new material, that's it. That's all of rotation. That's all of angular momentum. We're done. And tomorrow we're going to start on our last big unit, waves. So we're going to start with waves and oscillations. And then on Wednesday, we're going to do sound, which is a subset of waves. And then that will be it. That'll be the whole course. Hopefully we have time on Monday to do some exam review. I know the schedule says we got to do stuff on Monday, but I'm hoping to sort of compress things a little bit and make some time for exam review. Okay, if you're watching on YouTube, thanks for making it to the end. I'm going to stop the recording now, and then I'm going to take some questions from the live audience of who we have left. Okay, ciao for now.